Imagine a system that can think, learn, and make decisions on its own, just like humans. Sounds interesting, right? Welcome to Edu AI Verse. In today's video, we will explore fundamentals of intelligent agents, one of the most important concepts in artificial intelligence and agent-based modeling. This topic is very important because intelligent agents are used everywhere, from spam filters and recommendation systems to self-driving cars. By the end of this video, you will understand what intelligent agents are, how they differ from traditional software, types of environments in AI, and how agents think and act step by step. Let's get started. Intelligent agents are software entities that continuously observe their environment, adapt to changes, and make autonomous decisions. For instance, a spam email filter learns from past emails to improve its accuracy over time. Example: a spam email filter. It learns from past emails and improves accuracy over time. Light bulb's simple idea. An intelligent agent is like a smart student. It learns from experience and improves itself. Let's compare traditional software with intelligent agents. Traditional software is static and rule-based, while intelligent agents are adaptive and goal-driven, capable of learning from their experiences. Let's compare traditional software with intelligent agents. Small diamond: traditional software, static, behavior is fixed. Same input, right pointing arrow, same output. No improvement over time. Right finger example. Calculator: 10 plus 5 will always give 15. Small diamond: intelligent agent, adaptive, learns and improves. Changes behavior over time. Right finger example. YouTube recommendations. What you see today is different from last month. Light bulb key idea. Adaptation equals intelligence. Another important difference. Small diamond: traditional software, rule-based, uses if-else rules. No understanding of goals. Right finger example. Traffic light system. It changes based on time, not traffic. Small diamond: intelligent agent, goal-driven, focuses on achieving goals. Makes smart decisions. Right finger example. Self-driving car. Goal equals reach safely. It can slow down, change routes, or stop suddenly. Light bulb key idea. Agents think about what to achieve, not just what to follow. Traditional software follows predefined rules, while intelligent agents are goal-driven, choosing actions that maximize success. For example, self-driving cars evaluate multiple options to reach their destination safely. Unlike traditional software, intelligent agents can learn using machine learning techniques. They evolve by learning from past data, feedback, and experience, making them smarter over time, like modern spam filters that adapt to new patterns. In other words, traditional software cannot learn on its own. Right finger example. Old email filter. Needs manual updates, but intelligent agents learn from data, improve automatically. Right finger example. Modern spam filter. It detects new spam patterns itself. Light bulb learning makes agents smarter over time. An environment in AI encompasses everything an agent interacts with. It could be a room for a robot, a chessboard for a chess AI, or user messages for a chatbot. The environment shapes how an agent is designed. Static environments remain unchanged while an agent is deciding, with no time pressure. Examples include crossword puzzles and chess, where the environment is predictable and easy to handle. We can say that it is easy for agents because nothing changes. Dynamic environments change continuously, requiring agents to react in real time. Examples include self-driving cars and stock market trading systems, where fast decision-making is crucial. In deterministic environments, the next state is fully predictable, with the same action always leading to the same result. This predictability makes it easier to design agents for tasks like chess and Sudoku. Non-deterministic environments are characterized by uncertainty, where the same action may produce different outcomes. Agents in these environments, like weather prediction systems, require probabilistic reasoning.